and start the recording. So, just for the sake of other people who might watch this lecture later on YouTube, I am going to repeat the first question very quickly. Okay, so that I don't have to record the entire session again. So, just bear with me for 2 minutes. So, welcome to week 5 Wheel Mobile Robotics course. This week we will be looking at the localization and mapping assignment. Uh, this course is by Nptel, and this TA session I am doing as part of my PMRF duties. My name is Suraj Borate. I am PMRF PhD scholar from IIT Gandhinagar. And let's move on to question 1. Given a differential drive robot which localizes itself in work environment using the odometry based on wheel sensor readings. Okay, so here wheel sensor means the encoders, obviously. Select the deterministic errors that can be eliminated by proper calibration of the system. So when we say deterministic, it's something that we can predict accurately what is going to happen and such errors. So if you see the options, limited resolution during integration. So this is something like Euler integration step size. Uh, that is like we want to keep it small, but we cannot keep it too small because then the computational efficiency becomes very low. So that is not something in our hand. It has nothing to do with calibration, and it has nothing to do with the deterministic errors, right? So uncertainty in wheel diameter, yes, wheel diameter is not equal due to manufacturing defects or wear and tear, then we should measure it and we should input the proper values in the formula, right? So that can be measured. Variation in point of contact of the wheel is very difficult to find. Misalignment of the wheels, yes, that also can be corrected and calibrated, right? So unequal floor contact, yeah, that is not in our hands, right? That is something part of the environment. Okay, so the answer is B and D, wheel diameter and misalignment of wheels. So question 3, let's move on to the question, sorry, 2. So for a differential drive robot, the initial pose at A, so our robot is at A, the coordinates were 2, 3 and 25. Okay, and the robot moves to another point B. Okay, and given that the distance between the two wheels, so distance between the two wheels means the wheelbase, right? So this distance is one unit. Okay, and the right and left wheels transverse 3 and 2.5 units respectively. So the right wheel has traveled 3 units and the left wheel has traveled 1 unit. Okay, so how much the robot has traveled? Right, so that is the question. So how much the robot has traveled? So we know that the formula is delta S is equal to delta SR plus delta SL divided by 2. So we take the mean of the travel distance of the both the robots. Okay, and what you will get? 3 plus 2.5 divided by 2, that is 2.75. Okay, so answer is C, right? So yeah, so if you see you want the intuition of the formula, uh, you can always look at this book, like all this error propagation law is like well derived in SIGWORT, Autonomous Mobile Robots by SIGWORT, okay, or Introduction to Autonomous Mobile Robot. This book has all these formulas. In the lectures, mostly the formulas were used directly. But if you look at the book, then the proper derivation you will find. Okay. Uh, but in this course, a lot of things are being covered, so the professors cannot go into individual derivations. But yeah, please refer to this book. It's a wonderful book. Okay, Introduction to Autonomous Mobile Robots by Sigwart, Roland Sigwart. Okay. So delta SR plus delta S. Okay, so just to give, without going to much details, like I will try to use some intuition. So let's say that this is the delta theta angle the robot is traveling, and this is the delta S left and delta S r distance that the two wheels are covering. Okay, so what we want is what is the distance of the central arc that is going to. So this arc is delta SL and this arc is delta SR. Then we take the approximation of this, like delta SR plus delta SL by 2. Okay. So that is the idea over here. So okay, so let's move on to the next one. So what will be the change in the pose? Uh, Change the pose from point A to point B. Okay. So when we say pose, pose means position plus orientation. Okay, so we want to tell both, but here it seems the options which are given, it's only the position that they are asking. Okay, uh, so let us try to do this. So first of all, we need to find delta theta. Okay, how much the orientation has changed between the 2 points, and how do we find? Can anyone tell the formula for delta theta? Change in orientation. Hello. Okay, so let me just write down all the formulas in case you have. And these are very intuitive also, like it's not very difficult. Okay, pen is little bit not performing very well. So delta theta is equal to delta SR minus delta SL upon B, and delta X is nothing but delta S cos theta plus delta theta by 2, and delta Y is equal to delta S sine theta plus delta theta by 2. Okay, and what is delta S? Delta S is nothing but delta SR plus delta SL by 2. Okay, so we have to just use this, but then you should also think why delta S delta theta is this. So let me use some other color. Okay, so this is very just for the sake of intuition. Okay, so let's say the blue color line is the centroid, distance traveled by the centroid. This is the left wheel, this is the right wheel, this is our robot. Okay, so let's say that our body frame, it's traveling in this way, and this is the current theta, and this is our P, let's say A, and this is the B point. Okay, now when a robot moves on a circular arc, so there is this, if this angle is theta, what is this angle? Can anyone tell how much the angle made by the tangent with the chord? Can anyone tell? What is the angle? Is it theta? Is it theta or theta by 2? If this angle is theta, what will be this angle? So this is 90. This will be 90 minus theta. And this is also 90. Tangent is always perpendicular to the normal or the radius. So this will be also theta. Right? So what we are seeing here is, if this is the orientation theta of the robot, robot and the orientation changes by delta theta, then the turning is also by delta theta, because the tangent to this curve also turns by delta theta. Is everyone getting this? Who is here? Ardhra, did you understand what I am saying? Hello, can you hear me? Hello.
Yes, sir.
Yes. Okay. So yeah. So the tangent also turned by delta theta. So this is, if you see delta theta by delta t, then this is nothing but the angular velocity of the robot, right? And so we
Yes,
had
sir.
seen, yeah, and if we had seen this formula in the kinematics, that, see, if I am dividing this equation both side by delta t, what happens? See, this is omega, this is v right minus v left by b, and this formula we had seen earlier, right? So this is nothing but our kinematic model formula, where the wheel was related to the wheel transition matrix was there. Okay, so so this is the intuition. So the basic idea is that when the orientation is changing, the tangent is also rotating by delta theta. Okay, delta x and delta y are straightforward. It's just what v cos theta, v sin theta only, and we are updating theta with delta theta by 2. Okay, so this is like this kind of approximation. Okay, so this is the formula, and you just have to substitute the values and you'll get the answer. Okay, here for this the answer. Okay, if you substitute, uh, I think, let's, so can someone try to substitute the values and give the answer very fast? Okay, I have given you the formula, just substitute the answer. So we have already found delta S. Delta S for 2.75. Okay. Delta SR was given as, what was it given? Delta SR was 3. Delta SL was 1. Right. So B is 1. Distance between left and right wheel. You substitute the values here. You should get the value of delta X and delta Y. Okay. So this cannot be definitely the answer, because point Z axis, Z coordinate cannot change. Okay, it has to be 25 only. Okay. So let's check only one of them, like one coordinate. Let's say delta Y if we check. Okay, so delta S is 2.75, and sine of delta theta. So delta theta we have to calculate, that is 3 minus delta SL 1 by uh, B is 1. So it is 2. Okay. What is delta S? Delta Y is equal to delta S was 2.75 sine of. Okay, so I don't have scientific calculator over here, so let's use MATLAB. So basically, even you can do this. If someone can quickly put in calci and just tell me the answer, that would be nice. 2.75 into cos of 2.722. What is the mistake that we have done? Distance between the two wheels is 1 unit. Hello? Can anyone spot the mistake? Okay, apply this formula and do this. Come on. 2.75 cos of sine of theta. Delta theta was 2 plus delta theta by 2 1. Here it's coming 2.75. Okay, so let me just check my calculations. Just give me a minute. Hello? Yeah, so the given itself we have taken wrong, right? We did not take 2.5. The left wheel travel distance is 2.5, not 1. Okay, see the question is 2.5. We are taking it as 1. If you substitute the right values, you'll get the right answer. Okay, so here we put 3 plus 2.5, but here we did not write it as 2.5. So that is why the answer came wrong. So let me do it again quickly. So delta theta is equal to delta SR3 minus 2.5 divided by 1, that is zero point 0.5. Okay, and so what will be delta y? Delta y will be 2.75, that is delta s, into sine of 0.5 plus 0.5 by 2. And if I put in MATLAB, then I will get correct answer. Okay, so this is 0.5 plus 0.5 by 2. Okay, so it's approximately equal to 2. Okay, so the answer I think is 1.17, because that is the closest that I see. Okay, so just apply the formula. Okay, and then they say they find the y coordinate of the new pose of the robot up to 2 decimal places. So you just add the y plus delta y, then you'll get the answer for fourth. Okay, uh, what is y? Original y is 3. Okay, and the new delta y we got is 1.17, so we just have to add 3 plus 1.17. Okay, so let's move on to the next question. Okay, choose the true statement. Prediction update is based on updated belief state. Uh, Perception update decreases the uncertainty as the robot moves. Action update is based on prior belief state. And prediction update increases the uncertainty as the robot moves. Okay, so can you attempt this question? What is the answer? So the prediction update is based on updated belief state. Okay, so obviously we cannot, if the state is already updated, then what are we predicting, right? So it is based on the motion model, right? It's based on the motion model, not the updated belief state. So A is wrong. So perception update decreases the uncertainty. Yeah. So when you do the update of perception, the uncertainty of the robot decreases. Okay. Why? Because when the robot moves, of the robot, the motion model of the robot will uh, give us some information about where the robot will be. Okay. Action updated based on the prior belief state. Okay. So this is true. Okay. Because when you are doing the motion action update, at that time you need where the current belief of the robot is. Okay. That we need. Okay. Prediction update increases the uncertainty as the robot moves. Okay, so this is. Can you tell me what is this? Is it true or false? Prediction update increases the uncertainty as robot moves. Whereas here it's written prediction update decreases the uncertainty as robot moves. Okay, so here the key is that this is perception and this is prediction. Okay, so what is the difference between perception and prediction? Okay, so this is based on the motion of the robot and perception means the sensor measurement Z. Okay, so when the robot motion will help in, for correlating the perception. Okay, but the prediction uncertainty will increase if the robot moves. Okay, so that's the difference. So this is also correct and this is also correct. Okay, so BCD is the answer. Okay, so let's move on to the next question. If you have any doubt, you please stop me. Okay, the Markov assumption made in the Markov localization is given as. Okay, the only current sensor measurements are required for accurate localization. The current state is only dependent on previous state and its modes, recent actions and perception. Probability that a robot state estimate equals the robot actual state is maximized, tracks the robot and is inherently very precise and efficient. See, here also, if you see only current sensor are measured for accurate localization, that is wrong. Okay, because then what is the point, right? What is the improvement that we are making? If the current sensors are enough to localize. Okay, we have to use the past and information till where the robot was, right? Then only we can use the current measurements to update our belief. or update our understanding of the position of the robot, right? So here the important word is state. Okay, when we say state, it means that we only need the current action and current measurement. Okay, and the state represents the entire past history. Okay, so it's like saying all past measurements are and everything past action measurements are encapsulated in this state. Okay, so this is what is the Markov assumption. So the B answer is correct. Okay, so let's look at the remaining options. Probability that robot state estimate equals the actual robot state is maximized. No, Markov assumption has nothing to do with this. And yeah, so there is nothing like precise and efficient and stuff about Markov assumption. Okay, so it's a probabilistic met it leads to a probabilistic method. Okay, so it has nothing with tracks the robot and all. No, it's just some statement. Okay, so select the false statements. Okay, in Markov localization, to update the probability of all positions within the whole state space at any time requires a discrete representation of space grid. The required memory and calculation power has thus become very important. Okay, if the grid is used. So this is true, right? So in Markov, we need to know we assign probability to each and every possible state. So let's say this is 1, 2, 3, 4, 5, 5 cross 5 grid. Okay, so there are total 25. So initially, if you don't know where the robot is, then probability of each grid cell is 1 upon 25. Okay, and so if the grid cells are more, then we need lot of memory and calculation power. So that is true. Uh, so so Markov localization starts from any unknown position. So no, so initial state needs to be known, right? So it cannot start from any unknown position. In Markov localization, the recovery from ambiguous situation is not possible. Uh, sorry. So okay, sorry. So B is Markov localization starts from yeah. So we can have probability assigned to the position, right? So it doesn't need to be 100% known. Okay, so B is also true. Okay. In Markov localization, the recovery from ambiguous situation is not possible. Uh, so when we say ambiguous, it means that uncertain, right? And it deals with uncertain situations, right? So obviously the recovery is possible. So this is false. And Markov localization tracks the robot and is inherently very precise. So yeah, it has nothing to do with precise and definitely is not efficient because lot of memory and calculation is power is used. So C and D are false. So I hope this question is clear. Okay, ninth question. So for a robot moving in negative y direction in global coordinate frame and which uses control inputs to predict position estimates. So it's using the actions. For such a robot, its position estimate will have. Okay, so the variance equal in x and y directions, least variation in direction orthogonal to its motion, least variance in the direction of its motion, and variance will be greater in y direction. So, what do you think? Can anyone answer this question? Okay. So if there is lot of background noise, I really apologize for that. Uh, can anyone please answer this question? Hello, is anybody there? So, So the idea is that robot is moving already in negative y direction, right? And and it is using control inputs to predict the position estimates. Okay, so the word here is estimate. Okay, and what it is using is the control input. Okay, and that estimate is coming in the direction of the motion of the robot, right? Is it clear? So where the measurement or the the control inputs means what? The encoder data only. Okay, so how do you measure the control inputs? How much the encoder has rotated, or let's say you record the control inputs. Okay, I gave motion in y direction. Okay, someone is joining, it seems. Okay, so the motion is happening in y direction. So the update will happen in y direction, and that is why the uncertainty will decrease in y direction. And what represents uncertainty is the variance, right? So the answer is, okay, my pen is least variance in the direction of its motion. Okay, there will be maximum variance in the orthogonal direction because we don't have any data about it, right? Okay, choose the incorrect statement. Okay, so SLAM is a process by which mobile robot can build a map of an environment, and at the same time, okay, the light is also not proper today. So I'm out of town and I am taking the lecture. So for voice and lighting, okay, I cannot help. But okay, so bear with me for today's lecture. Lot of disturbance going on. So SLAM is a process by which a mobile robot can build a map of an environment and at the same time use this map to reduce its location. B option is in SLAM. Both the trajectory of platform and the location of all landmarks are estimated online without need of prior knowledge of location. So this doesn't make sense. Map can be there. It's not necessary that there is no knowledge of location. Okay. SLAM stands for simple localization, so it's simultaneous localization. So this definitely is an incorrect statement. Okay. This is an incorrect statement. In SLAM, only trajectory of platform is estimated online with need of prior knowledge of location. Okay, so not the only the trajectory, right? We also estimate the environment map. Okay, if it is only the trajectory, then it is just localization, not simultaneous localization and mapping. So D is also wrong. Yeah, both trajectory and location of all landmarks. This is right. Is not a false statement. Yeah, map also and location also. So this is also right statement. So the false statements are C and D. Okay, so just definition. So question 10, choose the statement that best suits for the prediction update of a robot. Okay, so can anyone, at least for the last question, attempt? Are you able to read the question properly or the font size is small or something? Please tell.
क्लियर है सर.
क्लियर है ना? तो अटेम्प्ट करो, पढ़ो इसको. ये मोस्टली थियरी क्वेश्चन है और although this it has lot of concepts together, in this particular week have come together. The assignment is mostly theory, but I would advise you to look up for the codes of how to code this. Okay, So if you see search slam, GitHub and all, Python from scratch, slam in Python from scratch or something like that, then you'll get lot of, because just by looking at the equations you won't understand. Okay. You will get the intuition कि okay motion update है तो uncertainty कम हो जाता है, like that. And the questions are also like that only. So we can just read the statement and answer. Okay, but to actually implement this is a task, and for that I would suggest, okay, look at people's code on GitHub, understand how the Markov and how the grid is updated. Okay, so those things you look. Okay, so the last question, please attempt. Tell me the answer. So which statement best suits for the prediction update of a robot? So when we say prediction update, it means that we are using the motion model. Okay. Okay. So when we say prediction update, it's like belief, right? XT, right? We need the position and the command. Okay. So we need actually the previous position and the command. Okay. Uh, this odometric input. So this is right. Sensor input, no, we don't need sensor input for prediction. We need sensor input for perception update. Okay, so sensor, see here, odometry is not called sensor. Sensor is for mapping the range sensor. Okay, camera, lidar, those things they are calling sensor. Encoders they are not calling sensor. Encoder comes as input command or what motion the robot is doing. Okay, so don't get confused. Okay, predicts its current position based on previous position and previous uncertainty. No. You also need UT, the command. Estimate its current position based on odometry and no. Yeah, odometry is right, but not sensor input. Okay, this sensor input is required in perception update. Okay, so that ends our,
Sir,
yes.
what is the
So
difference between saying estimates and saying predicts?
yeah, okay. So usually, so are you asking somewhere did you see the word estimate and predict? Or you are saying just based on, okay, see, this is not the difference. Estimates and predict is not the difference. Okay, the difference is here, odometric and sensor. Getting
Okay.
odometry,
So
yeah.
basically,
See,
in this
sense,
context, they mean the same thing.
yeah, estimate and predict is same only. There is no difference. Okay, you can use it interchangeably. But here, odometric input means the how much motion has occurred. So delta x, delta y. Okay, that or we can say that how much the left wheel has turned or right wheel has turned. Okay, so how much motion has happened. Whereas sensor input means okay, what the robot is seeing around it, what landmarks it is seeing. Okay, so this doesn't happen in prediction update. This happens in perception update. Okay, so that is the difference. Okay, okay. So any other doubts if you have, please let me know. I will be here for more time if you need me. you are saying something? Someone is saying. Your voice is not clear.
Odometric calibration
Odometric calibration question here.
error.
अच्छा ये वाला क्वेश्चन. हेलो. हाँ.
Yes,
आपका
sir.
बहुत डिस्टरबेंस आ रहा है माइक से. हेलो. हाँ बोलिए.
Odometric calibration error.
ओके. हाँ उसमें क्या? उसका मीनिंग जानना चाहते हैं आप? ओडोमेट्रिक कैलिब्रेशन एरर क्या? अच्छा ये वाला क्वेश्चन ना. See what happens is in odometry I'll tell. So odometry में suppose I have a robot like this, okay, and I ask it to move on a square. So it won't actually move directly on the square. What will happen is if you ask it to move straight 1 meter, it will move some off like this in some other direction. Okay, lengthwise also and orientation wise also, and then it will. So instead of this square, it will make this particular something like that, and it will not even reach back to the initial position. And there are multiple reasons for that. Okay, some reasons you can determine are deterministic, or you can find, right, like systematic errors, and some is beyond your control. Okay, that you cannot find directly. So for what you can find, you can calibrate. Okay, so for example, you. Okay, so what are the systematic errors that can take place? Maybe the wheels are of slightly different size due to manufacturing defect. Okay, or the wheels are not aligned properly. Center to center match नहीं है या फिर the axis is not proper. Okay, so such things will make the error have some trend. You can predict कि अच्छा, okay, because of this, let's say wheel being less or greater than other wheel, okay, every time this much error will come. That you can calculate, and then you can compensate for that. So that is called calibration, compensating the error. Okay, so that you can do, but some errors are like you cannot do anything about it. Like for example, the wheel is slipping on the ground. So on different part of the ground, due to point of contact will change due to roughness of the ground. You cannot predict where how much will be there, right? So that you cannot calibrate. Okay. So where you can compensate the error because the difference in the wheel size is constant. The cause and the effect will also be constant, and you can compensate it. Now how to compensate, and also there are papers on how to remove the systematic error in odometry and all. So you can refer to them. So there is this square test. You can look at like square test for odometry calibration. So that can improve the odometry, but odometry error cannot be completely eliminated because it also depends on these non-deterministic things like unequal floor contact, variation in contact point of the wheel, slip, etc. I hope that answers your question.
Thank you, sir.
Okay. Anything else?
Sir, actually, I joined in late. Can you just please move the slides one by one of all the questions? I just want
Which
to have a
one?
look at it.
Okay, I can go through the questions, huh? Okay. Okay, so this is one question. So if it's about the calibration, then this is about okay how much the robot travels from one place to another, how the position of the robot and orientation of the robot changes. So here we are using these formulas to solve how to check how much the robot has changed its position and pose. Okay. Then this is about again the perception and prediction that we talked. Then this is about Markov localization. So what is the definition of Markov localization and what it depends on? So we say that it depends on state and the action. So the state will encapsulate all the previous history. So you don't have to know all the commands and all the positions or the whatever state variables before the time. Only the current state is enough to tell. Okay, and the action at that time is enough to tell what will happen next. So that is what is Markov assumption. Okay, and the measurement also. Okay, then this is about telling that Markov localization is not very precise and efficient. Okay, uh, not efficient because in the grid we need to have probabilities for each and every cell, and the storage space and computational is very high, and not precise because it is a probabilistic approach, right? So and this question tells okay about the variance and uncertainty. So where there is more uncertainty there will be more variance. So more uncertainty will be there where there is least information, and the least information comes because of two reasons. One is either you do not have measurements, or you do not have know about motion, okay, in that direction. So here they are saying there was motion in y direction, so what, so obviously there will be a less uncertainty in y direction. Okay, so this is about the definition of SLAM, that both map and both the position of the robot is estimated. Okay, localization and mapping happen simultaneously. And this question is about what we discussed. Yeah, I think you were there for this question. Okay,
Okay, sir.
yeah.
Okay, sir.
Okay, in the chat I will post some YouTube link for SLAM, if you want to learn the coding of SLAM. So it is a very nice this thing where I learned from. Yeah, this one. Okay, so you can also look at this. This is a nice resource, and he has shown how to code SLAM. Okay. Uh, Please copy this and keep. And so this week this is just an introduction to just let you know about the terminology. So this and some definitions like Markov and all, but it doesn't go deep into how to implement. So please look at these lectures. Uh, this will be helpful. You know. And if you are using ROS, then SLAM can be implemented without, just by, using like running the Hector SLAM package or Gmapping package. Okay. But if you want to understand the algorithm, then you should look at this, the resource that I have sent. So any more questions?
Sir, I wanted to ask, since it is my first time being an NPTEL quiz, the final exam will be more of theory based or more of numerical based?
Yeah, so it depends on chapter to chapter. We do not know, right? It depends on, so one chapter may be more numerical, one chapter can be theory. So it's not something I can predict, and I'm not dealing with it directly. So I cannot tell anything about how the questions would come in exam.
Okay, so basically, if I am solving the assignments on time, so I am good.
Yeah, if you are doing the assignments on time, I think it would be good enough. But still, I think more than assignments, it's not about the exam. You should focus on the concepts that have been taught in the lecture. And if you don't understand something from lecture, you can ask us. If you are not able to answer, we'll take it up in the next session. Okay, but you also have to do, mostly it will be from lecture. If the lecture doesn't, whatever the lecture touches upon, that only will come in exam. Okay, nothing more than that or less than that. Or, yeah.
Okay, sir, got it.
Hmm. Anything else? So if there are no more questions, then we can wrap up. Uh, okay, so thank you for joining. See you in the next week. Uh, bye everyone. If you have any more questions related to previous weeks or this week also, you can ask in the next week. Uh, okay, see you. Bye. Thank you for coming.